Welcome to this explainer on the mechanical properties of fluids. Think of this as your ultimate study guide, bridging textbook physics and hardcore, real-world engineering. Whether you're a physics student gearing up for a big exam or just someone fascinated by the hidden forces shaping our infrastructure, you are in the exact right place. Okay, let's briefly run through the agenda. We're structuring these concepts logically. We'll start with pressure and static fluids, move into Pascal and hydraulic systems, speed things up with Bernoulli and fluid dynamics, tackle the sticky reality of viscosity in real fluids, and wrap the whole shebang up with surface tension and capillarity. Section 1. Pressure and static fluids, the foundations of fluids at rest. Let's get right into the profound forces these static fluids exert on their surroundings. Now, we didn't just figure all this out overnight. It's a massive historical progression. Back in 1643, Evangelista Torricelli completely changed how we view vacuums and pressure with his simple mercury barometer experiments, literally proving the atmosphere actually has weight. Then, in the 1650s, Pascal studied how fluid pressure transmits, and by 1738, Bernoulli was setting those fluids into dynamic motion. These early foundational breakthroughs were absolute game changers, sparking the evolution of measurement tools from basic open-tube manometers right up to the highly advanced pressure sensors we rely on today. Let's start with a core definition. Pressure is simply the normal force exerted by a fluid per unit area. P equals F over A. So the crucial takeaway here is that static fluids only exert force perpendicularly to surfaces. This means the smaller your contact area, the greater the impact. Think about a sharp needle. It pierces the skin effortlessly, right? But press a blunt spoon against your skin with that exact same force, and nothing happens. Also, unlike solid materials that can heavily resist shape changes, liquids offer barely any resistance to shear stress. Oh, and for your quick reference sheet, we measure this in pascals, which is just newtons per square meter. To put those pascals into perspective, standard atmospheric pressure at sea level is a massive number, 1.013 times 10 to the 5th pascals. That is over 100,000 pascals of constant, invisible weight pressing down on absolutely everything. Connecting this theoretical math to the real world is vital, even for something as routine as everyday household plumbing maintenance. When you're checking water pressure in a massive tall building or just bleeding a radiator at home, you are directly interacting with these static pressure differences. Let's systematically break down a practice problem to see how we evaluate the immense pressure forces acting on a submerged object, like the window of a submarine, where pressure ramps up drastically the deeper you go. Step 1. Identify the submarine's depth, say 1,000 meters, and the seawater density. That fluid density is absolutely critical for calculating not just pressure, but also buoyancy and displacement. Step 2. Calculate the gauge pressure using density times gravity times height. Finally, step 3. Multiply that pressure by the window's precise area to find the total force. And let me tell you, at 1,000 meters down, that force is absolutely staggering. Moving right along to section 2, Pascal and hydraulic systems, multiplying force. Here's where the physics gets incredibly powerful. Pascal's law states that pressure applied to an enclosed fluid is transmitted undiminished to every point. Basically, Pascal realized that if you apply external pressure to a confined liquid, it distributes equally everywhere. Why? Because liquids are virtually incompressible. Push down on one part of a fluid, and it instantly transmits that exact same pressure to every single corner of its container. It's a brilliant way to multiply force. Let's step through the math to see how engineers manipulate this to do heavy lifting. Step 1. Determine the areas of your small piston and your large piston. Step 2. Apply Pascal's law, setting the pressure of the first equal to the second to relate those forces. Step 3. Solve for the small force needed. It is mind-blowing, but you can literally lift a 1,350 kilogram car by applying just a tiny fraction of that force to the smaller piston. This step-by-step logic directly dictates the mechanical designs behind hydraulic lifts and automotive brake systems. It's exactly how engineers optimize large-scale hydraulic systems worldwide. Section 3. Bernoulli and fluid dynamics. Fluids in motion. Let's turn the tap and get things flowing. When analyzing system designs, engineers have to clearly differentiate between the theoretical math of an ideal fluid, which is incompressible, frictionless, and steady, and the harsh, viscous reality of an actual fluid. If you assume a fluid is perfectly ideal out in the field, you are asking for trouble. Real fluids have internal friction, which inevitably leads to viscous resistance and energy lost as heat. Let's compare laminar versus turbulent flow. There are key visual cues and environmental factors out in the real world that cause smooth streams to abruptly turn chaotic. In laminar flow, you'll see perfectly parallel streamlines, and the fluid layers slide past each other at a steady speed. But throw a rock into a stream, or just push a fluid past its critical speed, and boom, you trigger a transition to turbulent flow. The visual indicators immediately switch to crossing streamlines and whitewater whirlpools. As an engineer, that is a totally different design challenge. Now for Bernoulli's principle, which tells us that along a streamline, the sum of pressure, kinetic energy, and potential energy per unit volume remains constant. The big takeaway here? When a fluid accelerates, its streamlines crowd tightly together, and the internal pressure actually drops to conserve energy. Picture a wide pipe suddenly narrowing into a bottleneck. As the fluid speeds up to squeeze through, those streamlines crowd together. To keep the total energy balanced, the pressure inside that fast-moving fluid literally has to decrease. And this principle is exactly how we keep massive Boeing aircraft suspended in the sky. The specific curve of an airplane's wing forces the air on top to move faster, which drops the pressure above and creates dynamic lift. Fluid density and velocity differences drastically impact vehicle performance in both aerospace and maritime environments. We also see this in sports with the Magnus effect, where a spinning cricket ball creates uneven pressure and curves midair. We even applied Torricelli's law of efflux to calculate rocket propulsion exhaust using these very same rules. Section 4, Viscosity in Real Fluids, Internal Friction. Let's introduce the messy reality of mechanical friction. Viscosity is the internal resistance to flow between fluid layers. It's the exact reason water flows effortlessly through city pipes, while thick industrial sludge demands massive, high-efficiency pumping systems. But hey, it's not just an industrial issue. Viscosity literally dictates the operation of common household appliances every single day. Think about it. It impacts the pumping efficiency of your washing machine, the specific flow rate of the refrigerant inside your fridge's compressor, and even the spray intensity your dishwasher jets need to actually get your plates clean. Consider the contrasting temperature behaviors between liquids and gases. This is absolutely critical for maintaining machinery across different climates. For liquids, when you turn up the heat, viscosity actually decreases, like warming up cold maple syrup so it flows faster. But for gases, it's the exact opposite. Heating a gas increases random, chaotic molecular collisions, meaning its internal resistance, and therefore its viscosity, actually increases with heat. Pretty counterintuitive, right? I want you to remember this as a major tip for interpreting data. Precise viscosity calculation is the absolute key to minimizing long-term component wear and preventing catastrophic machine failure. If a fluid is too thick, an industrial pump is going to overwork and burn itself out. But if it's too thin, it might not provide enough lubrication. Calculating this correctly is quite literally what ensures the durability of heavy industrial machine parts over years of operation. Finally, Section 5, Surface Tension and Capillarity, the boundary layer. We are looking at the unique phenomena where fluids meet air or solid materials. Surface tension is the extra surface energy per unit area that minimizes a liquid's surface area. Because the molecules right at the surface don't have liquid above them, they cling extra tightly to their neighbors beside and below them. This molecular attraction creates an energetic skin that actively tries to shrink its own surface area. It's the precise reason why raindrops pull themselves into perfect little spheres and why certain insects can literally walk right across the surface of a pond. These boundary properties mediate daily life everywhere. Take capillary action. Fluid density and flow properties allow living plants to pull water straight up against gravity to feed tall trees. Meanwhile, in our own human bodies, fluid circulation relies heavily on pressure gradients generated by the heart to keep blood moving. Even basic household soaps work by chemically reducing surface tension so water can penetrate and clean fabrics better. And don't forget the meniscus. Those changing curves in a test tube rely entirely on contact angles between the fluid and the glass. So I want to leave you with this provocative thought. If Bernoulli's elegant equations rely on frictionless flow, and we know for a fact that all real-world fluids have viscous resistance, how do engineers confidently design the systems we trust our lives with every single day? How do we bridge that gap between perfect textbook math and our beautifully chaotic reality? Well, it's the careful, brilliant application of these very principles that turns theoretical formulas into safe submarines, soaring airplanes, and functioning modern cities. Keep questioning, keep calculating, and I'll catch you in the next explainer.